Hey everyone, and welcome, 8th graders. I am absolutely thrilled you're here for today's explainer, the neighborhood of elements, discovering wisdom in chemistry. Now, I know exactly what you might be thinking when you hear the word chemistry. You're probably picturing a giant, complicated poster on a classroom wall. Actually, scratch that. You're probably picturing a total nightmare of random letters and numbers that you just have to memorize, right? But what if I told you that chemistry really isn't a chore at all? What if, instead, it's this beautifully organized system? Today, we're going to look at the periodic table not as some random list of elements, but as a vibrant, incredibly well-planned city. And you're about to get the master key to the whole shebang.
Okay, let's dive into this because this is the question literally every chemistry student asks. How on earth do you master this subject without memorizing every single tiny detail about all 118 elements? Well, the secret is you don't memorize it. You learn to read it like a map. Once you understand exactly how this map is drawn, you won't ever need to guess how an element behaves. You'll already know, just based on where it lives in the neighborhood.
And this idea of an underlying map points us to a really profound concept. By wisdom, the Lord laid the earth's foundations. You see, the periodic table isn't some human invention. It's a human discovery of an ordered foundation that was already there. Recognizing the patterns built into the very fabric of the universe, that is a deep, profound form of wisdom. When we learn this order, chemistry goes from being a confusing mystery to becoming totally, beautifully clear. So, let's hit our first section, families and neighborhoods, the structure of the table. And this brilliantly illustrates the big idea behind the entire map. You see, the table has two main directions. The vertical columns are called groups. You can think of these as tight-knit chemical families. Everyone living in the same vertical column shares a ton of the same chemical DNA. They act alike and they react alike. Then we have the horizontal rows, which are called periods. Think of a period kind of like a neighborhood street. As you walk down that street from left to right, the characteristics of the houses, or the elements in this case, shift in a very predictable, logical flow. Moving right along, it's time to meet the chemical families. Now, what's really fascinating is just how distinct these family personalities are. Take group 1, the alkali metals. These guys are the hyperreactive soft metals. They have exactly one valence electron, that's just an electron hanging out in their outer shell, and they are absolutely desperate to lose it. That makes them incredibly reactive. Next door, in group 2, we've got the alkaline earth metals. They're also reactive, but, a bit more chill, moderately reactive, typically forming ions with a 2+ charge. Then we jump way over to the other side to group 17, the halogens. These are highly reactive nonmetals holding on to 7 valence electrons, frantically looking around for just one more. And finally, sitting comfortably at the far edge in group 18, we have the noble gases. They have a completely full outer shell, meaning they are totally unbothered, completely unreactive, and perfectly content just exactly as they are. Let's see how this all builds across those horizontal neighborhoods. If we take a walk across a period row from left to right, we witness this fascinating transition. We start in a neighborhood of pure metals, but as we walk right, those shiny, highly conductive metals slowly fade into metalloids, elements that are kind of caught in the middle. Finally, they transition entirely into nonmetals. If you actually measure it, things like heat and electrical conductivity steadily drop the further right you walk. It's just this beautifully predictable gradient. All right, next section, predicting the real world. So I'm going to throw a rapid-fire question at you right now. Think about the map we just explored. Where does chlorine belong? And based on its address, what does it tend to do? Take a quick second. Any guesses? Well, if you said it's a halogen, you absolutely nailed it. Chlorine lives in group 17. Because it's in that specific family, we instantly know it has 7 valence electrons. We also know its personality, right? It is super eager to pick up just one more electron to complete its shell. Because of this, chlorine literally loves to bond with metals to form salts. Yeah, like sodium chloride, the exact salt you put on your French fries.
Awesome. Let's try another one. Let's compare two different metal families. Which one of these is going to be more aggressively reactive? Sodium, sitting in group 1, or magnesium, sitting right next door in group 2?
The answer is sodium. And the logic here is brilliantly simple once you actually know the map. Sodium is in group 1, meaning it only has to drop a single, lonely electron to become stable. That's a super easy, incredibly fast process. Magnesium, over in group 2, has to get rid of 2 electrons. Tossing away 1 electron is just naturally way easier and faster than tossing away 2, making sodium's chemical reactions far more vigorous.
Okay, one last rapid-fire test. Let's think about that notoriously aloof element. Neon. Why doesn't neon readily form chemical compounds with anyone else?
Exactly. Neon is a group 18 noble gas. Its outer electron shell is totally packed, completely full. It has zero need for any more electrons, and it definitely doesn't want to give any away. It's safe, it's stable, and it is highly unreactive. And this isn't just fun trivia. This behavior makes noble gases incredibly useful in the real world for creating safe environments. We're talking inside bright light bulbs or as a protective shield during intense metal welding, where that stability is absolutely key.
So the crucial point is knowledge, morality, and peace.
Let's look at the real-world applications of all this. Because we can predict reactivity, chemists know exactly what not to mix. That literally prevents highly unsafe, explosive reactions in the lab. It also guides civil and electrical engineers in choosing the absolute perfect materials, like knowing for sure which metals will conduct electricity best for wiring, or which will be strong enough to use as structural beams. It even drives modern technology, helping us design longer-lasting, far more efficient batteries for our phones and cars. Understanding this map keeps people safe and honestly builds the modern world.
But let's take this one step further. We've talked a lot about gaining knowledge and understanding the rules of chemistry today. But as the Heroesmart Academy Godly Learner series reminds us so powerfully, education without morality will hurt. Really think about that for a second. What is the point of being incredibly smart, of knowing every single chemical reaction, if you use that education to continually make bad choices that hurt yourself or others? Real wisdom requires a strong moral compass to guide that education. When we look at chemistry, we see a universe built on incredible order and profound wisdom. And that exact same order applies to our own minds and hearts. Romans 8:6-7 offers a promise of deep peace of mind to everyone who keeps their thoughts aligned spiritually and morally. Just as the noble gases find perfect stability in their completely full ordered shells, we find incredible stability and peace when we align our educated minds with spiritual wisdom.
So I leave you with this final, provocative thought to carry with you out of today's explainer. You now know exactly how to read the brilliant map of the elements. You have this knowledge, but what are you going to do with it? Will you use your education simply to pass a chemistry test, or will you pair it with deep moral wisdom to build a safer, better world for absolutely everyone? The choice is totally yours. Keep asking those questions. Keep looking for those patterns. And I will see you in the next one.